Hello, this is Mr. Waitman. Today's video is a subtopic of stoichiometry. We're calling this the mole ratio. First thing, stoichiometry. This is the calculation of the relative quantities of reactants and products in a chemical reaction. That is to say, depending on how much you put in, you'll be able to predict how much will come out. Or, if you know how much came out of a reaction, you could predict how much went in. We're going to use a technique called up, over, and down. This is just a simple graphic organizer to help you keep track of what you know, what you're figuring out, and how to get there. So let's get right into it. Let's start applying the molar ratio. We're going to use this idea of the over, that is, using the ratio that we find in a chemical equation. So let's start with this reaction. We've got methane gas, and if we were to combust methane, it would require oxygen. It would produce carbon dioxide, and it would produce water. But looking at this reaction, we know it's not balanced. So the first step is we need to balance our chemical equation. It's going to look something like this. Now what this is representing is the actual molecules involved. So we know that for every methane molecule that we have, we would require 2 oxygen, and it would produce 1 carbon dioxide, we see that here, and we've got our 2 water molecules here. So let's just make that all black and a proper balanced chemical equation. Now we've left out states here. It's not particularly relevant for the concept that we're doing, but we recognize that proper form we would include those. So if we've got our balanced chemical equation, we have a mole ratio. That is to say, the actual coefficients that we see in front of each of these chemical formulas represents a mole. So in this one, it's implied that I have 1 mole of methane, I have 2 moles of oxygen, 1 mole of carbon dioxide, and 2 moles of water. It's a ratio of 1 to 2 to 1 to 2. And again, I could do that graphically, showing that I've got my one molecule of methane, my 2 oxygen, my 1 carbon dioxide, my 2 water. Okay, how does this over piece come in? Well, we don't always want to know every substance in a reaction in a question. Sometimes we need to figure out how much of a particular reactant we would need to make a reaction occur if we had a given amount of one of the other reactants. So let's go back to the same reaction. We'll get familiar with it. If I was to look at the coefficient in front of the methane, it's implied that it's a 1. If I wanted to determine how many moles of oxygen I would require, this is where the over comes in, I recognize that it's a 1 to 2 ratio. Now, here we're just exemplifying the actual ratio. We'll get into it a bit later when we have a different number of moles other than that found in the ratio. We could use the same to come up with a ratio of methane to carbon dioxide. It would be 1 to 1. And we could use that same technique to look at a ratio of methane to water produced, which is 1 to 2. But this isn't always in one direction. It's a relationship. So it's not just relationships of reactants to products, but rather it can be a relationship of products to products, or products to reactants, or reactants to reactants. In this example, I'm looking at the number of moles of water produced. So for every 2 moles of water produced, I would have required 2 moles of oxygen. So again, this is really just showing a relationship between a whole bunch of substances in a reaction. Okay, next video we're going to actually get into applying this ratio.